When you think of a medical scan, you probably picture something like a photo, right? Just a picture of what's inside your body. But what if I told you it's not a picture at all? It's actually more like a blueprint, a really precise, data-rich map of you. So let's peel back the layers and see what's really going on in there.
Okay, just take a look at these two images for a second. On the left, you've got an X-ray, and it's telling a really clear story, right? There's a broken bone in that hand. Super simple, super direct. But then, on the right, you have an MRI of a brain, and whoa, that is a vastly more complex landscape of tissues and structures. I mean, they're both pictures from inside the body, but they're speaking completely different languages.
So that really brings us to the big question, doesn't it? How in the world do we get these incredible images, and what makes them so different from each other? That's what we're going to dive into. Let's break it all down. For most of human history, if you wanted to see inside a living person, there was really only one way to do it, with a scalpel. The biggest challenge for medicine has always been trying to see the invisible, to figure out what's wrong without having to do invasive surgery. And medical imaging, well, that was the revolutionary answer. And our source material really nails it when it says medical imaging is a cornerstone of modern medicine. It's truly the bridge that connects the super complex physics of how these machines work to the actual practical job of healing people. So the question is, how does a doctor decide which scan to use? Well, it's kind of like having a toolkit, right? You wouldn't use a hammer to turn a screw. It's the same idea. Doctors have this whole range of imaging tools, and they have to pick just the right one for the job. And these tools, they're basically sorted in two main ways. Okay, so the first big difference is anatomical versus functional imaging. Anatomical imaging is all about the structure. It's asking, what does it look like? It's going to show you the shape, the size, the physical layout of your organs and bones. But functional imaging, that's totally different. It's about the process. It's asking, how does it work? It's measuring things like blood flow or brain activity or your metabolism. And this right here is a perfect example of what I'm talking about. On the left, that standard MRI gives us this beautiful anatomical map of the brain structure. But on the right, that's a functional MRI, an fMRI, and it shows us the brain in action. See those bright spots? Those are areas lighting up with more blood flow, more neural activity. It's literally the difference between seeing a map of a city's streets and seeing the actual traffic moving through them. It's pretty cool. All right, the second big way to categorize these scans is all about the energy they use. You have ionizing versus non-ionizing radiation. Now, ionizing sounds like a fancy word, but all it really means is that it uses high-energy waves, like in X-rays and CT scans. They have enough power to literally knock little particles out of your atoms as they pass through. And that's what lets them create such incredibly detailed images of dense stuff, like bone. On the other hand, non-ionizing radiation, that's what's used in MRIs and ultrasounds, it uses much lower energy, which makes it safer. So there's this constant trade-off, More detail often means more energy. And this diagram just illustrates that concept perfectly. See the whole electromagnetic spectrum laid out here? Way over on the right, in that ionizing part, you've got your heavy hitters, X-rays and gamma rays. But then look way over to the left, in the non-ionizing section. That's where you find the much, much lower energy radio waves used in things like MRI. It's all about picking the right tool, the right energy level, for the right job. Okay, so we've covered the different kinds of tools in the toolkit, but now we get to the real heart of this whole thing. This is the big idea, the shift in thinking that changes everything. Because a medical image isn't what you probably think it is. I want you to just let this one sink in for a second. These images are not pictures. They are quantitative data. They are visual representations of these enormous data sets. Every single point in that image you see is actually a number, a piece of data that a computer has turned into a shade of gray or a pop of color. So how does that work? Well, it starts with something called a voxel. Now, we've all heard of a pixel, right? That tiny little 2D square of color on your TV or phone screen. Okay, now imagine stacking those pixels up, like Lego bricks, to build a three-dimensional object. Each one of those little Lego bricks, that's a voxel. It's a volumetric pixel, a tiny little 3D cube of pure information. And this makes it so much more clear. When you lay a grid over the scan like this, you can really see it. The image is just a huge collection of these data points. The scanner measures a value for every single one of those little cubes, those voxels, and then a computer assigns a brightness to it. So a voxel that represents bone gets a bright white value. A voxel for soft tissue gets a shade of gray. It's literally like a paint-by-numbers project, but on an absolutely massive three-dimensional scale. Okay, so if the image is just a giant grid of numbers, how does a surgeon know that the voxel at, say, position 100 by 250 by 80 is a specific crucial part of a patient's brain and not just empty space? Well, you need a map. You need a coordinate system. You basically need a GPS for the human body. And it turns out there are actually two systems working together here. The first one is called the Image Coordinate System, or ICS. The easiest way to think about this is like a spreadsheet. The ICS is just the cell address, like cell A1 or C5. It tells the computer where a piece of data lives inside the digital file, but, and this is the important part, it tells the doctor nothing about where that point is inside the patient's actual body. Okay, this is where the real magic happens. The second system is the Patient Coordinate System, or PCS. And what it does is it maps that simple spreadsheet grid onto the patient's actual anatomy. It uses the standard directions doctors use, left to right, anterior to posterior, which is just a fancy way of saying front to back, and superior to inferior, or head to toe. This is the body's true GPS. This is what makes a scan something a surgeon can actually use. And this visual just puts it all together beautifully. On the left, you've got that raw digital grid, the ICS, the spreadsheet. On the right, you have the actual medically useful map of the human body, the PCS. The whole ballgame, the really critical work, is translating every single one of those little data cubes from its spreadsheet address on the left to a precise GPS location inside the body on the right. So how do you keep all this information together? I mean, you've got millions of these data voxels, plus all the GPS data that tells you where each one belongs in the body. You need a special container, right? A standardized file format, a universal language that all the medical equipment in the world can speak and understand. And that language is called DICOM. A DICOM file is basically just a really smart container. And as you can see in this diagram, it's pretty simple. It has two main parts. You've got the data set, which is all the raw image data, all those numbers for the voxels. And then you have the header. That's all the other important info, the patient's name, the date of the scan, and, crucially, all the data needed to link the image grid to the patient's GPS coordinates. So why does any of this matter? Well, the most important thing is that DICOM provides standardization. It means a CT scanner in Tokyo can send an image to a doctor's computer in Toronto, and all of that critical spatial information stays perfectly intact. It's what allows hospitals to manage millions of these images in their systems, which, by the way, are called PACS. Think of PACS as a giant, secure library for all these medical blueprints. And DICOM? That's the universal language that keeps the entire library perfectly organized. So why have we gone so deep into all this stuff about data and voxels and coordinate systems? Well, here's the payoff. Because this entire framework, this whole idea of the body as a precise digital map, is the absolute foundation for the future of medicine. And that future is artificial intelligence. See, an AI algorithm can't just look at a picture the way you and I can. It needs numbers. It needs cold, hard data. It needs the exact coordinates of a potential tumor so it can measure its volume with perfect precision, track its growth over time, and compare it against thousands of other cases it's learned from. Without that GPS for the body, the AI is completely blind. And this right here is really the key takeaway of this whole explainer. It boils down to this. The coordinate systems, the GPS, they answer the question of where. Where is this thing located in the body? And then artificial intelligence comes in and provides the interpretation. It analyzes the data at that specific where to answer the question of what. What is this thing? It's location and interpretation, and they have to work together. So think about how far we've come. We've gone from just blurry pictures to these incredibly data-rich, fully navigatable blueprints of our own biology. And that just leaves us with one last really fascinating thought to chew on. If our bodies are now precise digital maps, what new territories do you think we'll discover next?